Now coming to the second property of the nerve is property of conductivity. That means an action potential that has been generated in the nerve is conducted throughout the length of the axon in one direction, that is present normally. But if we talk about experimental condition, the direction of propagation can be bidirectional. So, impulse conduction in a nerve can occur through the unmyelinated nerve axons, or it can occur in the myelinated axons. We can also classify the conduction of the nerve impulse as orthodromic and antidromic. So normally when an action potential is propagated in one direction, that is usually the nerve impulse from the receptors or the synaptic junction along the entire length of the axon to its termination. This is orthodromic conduction, as you can also see in this figure. And when the conduction of the impulse occurs in the opposite direction, anti, as seen in the sensory nerve supplying the blood vessel, it is called as antidromic conduction. You can also see in this figure the antidromic from the periphery towards the central receptors. So let us first talk about the propagation of action potential in an unmyelinated axon that does not have any myelin sheath. So whenever there is stimulation by a threshold stimulus, it results in a generation of action potential, and the nerve site is depolarized. As we can see here, it is more positive on the inside of the membrane as compared to the outside state of depolarization. Now what happens? A circular current flows from the depolarized area to the neighboring area so that it also reaches up to the level of firing. The second or the new action potential which is generated creates a local current that is flowing ahead of the previous site. You can see here. So this successive depolarization of the neighboring areas occur, and this results in the propagation of action potential. So the action potential in an unmyelinated nerve follows three steps. One, that is generation of the local area for the current, and then its successive propagation. The first is the establishment of the local circuit current. Once the membrane has been depolarized, we know that both extracellular fluid and the intracellular fluid are conductive to electricity. So a current will flow from the positive polarized area to the negative activated area through the extracellular fluid, and a reverse direction is followed in the intracellular fluid. Look in this figure. You can see the direction are reversed, clockwise and anti-clockwise for the intracellular fluid and the extracellular fluid. So once this local circuit current is existing, the resting polarized state to the depolarized state, it results in the current sink. So next, a fresh area of depolarization is formed. So a new action potential is produced, which in turn depolarizes the neighboring area which is ahead of it. Thus, due to successive depolarization of the neighboring area, area 1, then area 2, then area 3, the action potential is being propagated along the entire length of the axon, and this conduction is known as electrotonic conduction. The magnitude of action potential does not change. It remains constant because the number of potassium and the sodium channels are uniform throughout the length of the axon. So once initiated, the moving impulse cannot spread in a reverse direction. Why? Because the proximal site is in refractory state, and thus the conduction of the impulse carries on to the distal site, that is, it goes on depolarizing the neighboring area. Thus the direction of propagation will be unidirectional, and it is in the direction of the current flow in the nerve fiber. Okay, and then after some time there will be a phenomenon of repolarization, because we know that sodium channels are fast to open and fast to close, and potassium channels are slow to open. So once they start opening, there is a phase of repolarization, and the area which was depolarized first will also be depolarized first. Thus repolarization is also propagated following the wave of depolarization. This local current flow is unidirectional in nature. So we have a wave of depolarization and also a wave of repolarization. So this slide focuses on the ionic basis for the unmyelinated nerve conduction or the action potential in an unmyelinated nerve fiber, the generation of action potential in that nerve followed by the wave of repolarization shown by the potassium currents in green. Then this action potential is being propagated in the neighboring areas and this wave is carried forward throughout the length of the axon. The propagation of action potential in an myelinated axon is different from an unmyelinated fiber. Here the conduction is known by the name of saltatory conduction, where saltare means to jump. So there is jumping of action potential from one node of Ranvier to the next node of Ranvier, and this mode of conduction of action potential leads to the rapid propagation of the nerve impulse. Hence, we can conclude on this point that the nodes of Ranvier are the site for the genesis of action potential in a myelinated nerve fiber because the myelin that is wrapped around the axon many a times acts as an insulator and does not allow for the free flow of ions across the membrane. These nodes of Ranviers, which are present at a distance of 1 millimeter for approximately 1 micrometer, have high voltage gated channel in density. If I talk about the initial segment, they are just 250 to 500 sodium channel. But when we talk about node of Ranvier, the number of sodium channels are 2000 to 12,000 in number, leading to the regeneration of the action potential. Therefore, we can say that these nodes of Ranvier are acting as current sinks. The first step that occurs in conduction of impulse in a myelinated nerve fiber is same as that of unmyelinated fiber. There is a stimulation of a polarized axonal membrane with the threshold stimulus that leads to the generation of action potential, and the site is being depolarized as you can see in this figure. So the next step that comes is step that is propagation. The local graded potential is then transmitted along the axon from one node of Ranvier to the another node of Ranvier through the intracellular fluid. So the problem is that these local graded potential will decay. We know that the graded potential decays over time and space. So the decay is 37% of the maximal at the distance of 3 millimeter. However, the node of Ranvier is present just at a distance of 1 millimeter. That results in very less decay of the current, thereby leading to the stimulation of voltage gated sodium channel which are present in great number at the next node of Ranvier. That results in the regeneration of the action potential. It is not the same action potential as it was in the previous node, but the action potential here has been regenerated because of the sodium channels which are present here. So this is known as the saltatory conduction with regeneration of action potential at each node of Ranvier. So the successive depolarization waves then move the action potential rapidly through the nodes of Ranvier to the nerve terminal. The conduction velocity of the nerve is highly variable, as we had also seen in the Langes and gases classification. A fibers have a maximum conduction velocity. A alpha may be having a conduction velocity of more than 100 meter seconds, whereas type C fibers, which are unmyelinated, may have a conduction velocity as little as 0.25 meters per second. So the conduction velocity is dependent upon different factors. One of them is temperature. A decrease in temperature leads to the further decrease in conduction velocity. Then when we talk about the width of the axon, the greater the width of the axon, the faster is the conduction. This is so because the resistance that is offered by the exoplasm decreases with the width of the axon. It is inversely related. The third is the myelination. Myelination increases the axon diameter as well as the mode of conduction of an impulse in a myelinated fiber is saltatory conduction. So both these factors lead to an increase in conduction velocity. There are certain factors which cause block of nerve conduction. We know about local susceptibility to local anesthetic, hypoxia and pressure. Type C fibers are more affected for local anesthetic. Hypoxia affects type B fiber and pressure is affected on type A fibers. So these three factors are responsible for conduction failure in a nerve. Beside that, demyelination is also responsible for conduction failure. It is not unlike the unmyelinated fiber, the demyelinated axon does not have sufficient sodium channel on its internodal segment, and therefore it is incapable of generating closely spaced action potential. So what will happen? There will be decay of the action potential before its regeneration. So even a rise in the body temperature as occur in the fever, it predisposes to conduction failure in a demyelinated neuron.